Okay, so we've introduced the idea of the SN1 reaction that goes through a carbocation and then undergoes substitution to create a new product. We've introduced the idea of an SN2 reaction where both of those steps kind of happen at once. We add our base or our nucleophile and we lose our leaving group in the same step, make a bond and break a bond all in the same step. So SN2 is a one-step reaction, SN1 is a two-step reaction. Right? And so now the question is, when do we use a one-step mechanism? When do we use a two-step mechanism, right? When is SN2 the reaction that we want to do, and when is SN1? And the answer boils down to steric repulsion. So, second, there we go. SN1 versus SN2. SN1 must have a stable cation. Right, and how do we get stable carbocations? We add more stuff around there. So if you have a tertiary or secondary carbon, right, these are where SN1 reactions can happen. SN1 can happen here. Right, so if we have, wow, right, if we have something like this, right, then we have a leaving group attached to that tertiary position, right? We would look at this and say, okay, SN1 can happen here because we could lose this leaving group, make a carbocation, and go onward, right? SN2 reactions want to minimize steric repulsion. I think this is a little bit harder to kind of wrap our head around as to why this is, but think about in an SN2 reaction, the bond making and the bond breaking are all happening at the same time, right? So you have your nucleophile coming in, you have your leaving group going out, and so these things need to kind of organize themselves in such a way that the nucleophile can come in and the leaving group can leave kind of at the same time in order for nothing to run into each other. Right? And when we say run into each other, what we mean is you're going to get electron-electron repulsion. Your base is coming in, your base has got a whole bunch of electrons because it is, right, it's sharing those electrons with the carbon atom where this reaction is happening. And the leaving group has a whole bunch of electrons because it's a conjugate base that's taking electrons with it as it leaves. Right? And so you have two kind of things that are reacting and both have a whole bunch of electrons and they're going to repel each other. And so what happens in an SN2 reaction is one thing that happens is these two come in opposite each other. So we saw this in the reaction of the bromonium ion, right? When the bromine, so if we're talking about bromination, when the bromine comes in to react with the bromonium, it comes in from the opposite side that the bromonium ion is. So if your bromonium is wedged, the bromine comes in as a dashed bond. Right? That's an SN2 reaction. They always have to come in opposite each other because they each have so much electron density on them that they will repel each other otherwise. So they come in 180 degrees from each other. That's one thing. The other thing is all the other stuff that's attached at that carbon is also going to have electron density. And so if we have a tertiary carbon, right, there's a whole bunch of electrons in each one of those bonds. If we have a carbon that's connected to three other carbons, every one of those carbon-carbon bonds has electrons in it. Each one of those carbons that's connected to our reactive carbon is going to have more bonds, and those bonds are going to have electrons in them. And because we have, again, two reactants, the leaving group and the nucleophile or base, right? Because we have two reactants that are both very electron rich, they're going to be very sensitive to the amount of electron density that they have to kind of move past to get to that reactive position. And so SN2 reactions are very, very sensitive to steric repulsion, and they want to minimize steric repulsion. And so SN2 reactions happen at um, methyl groups. So if you have like methyl iodide, right, this is the absolute bare minimum of steric repulsion. This carbon has no carbons attached to it, right? That's probably the best. Primary is good, secondary is okay, tertiary does not happen, right? So methyl groups, primary groups, and secondary groups, SN2 can happen here. Right, so if we have whatever, 1 bromobutane, and we looked at this, this one would be an SN2 reaction, every time. Well, this one would be an SN1 reaction, because notice this is a tertiary position, and so tertiary is go for SN1, no go for SN2. Primary, right, we have a primary carbon here, tertiary over here. We have a primary carbon here in the SN2 one. Primary is go for SN2 and no go for SN1. And so if we look at where our leaving group is attached, we can sometimes predict what type of mechanism will happen. Now, of course, the problem is the secondary carbon, because SN2 reactions can happen at secondary carbons and SN1 reactions can happen at secondary carbons. And so the secondary carbon is where we struggle a little bit. So the first thing to determine in SN1 versus SN2 is find the leaving group. The leaving group is almost always a halogen or an alcohol plus acid, right? So if you have, for example, if you have, oops, and then you see H plus in there, right? You can make this carbon into a good leaving group because you can make it into OH2 plus, whose conjugate base is water, right? So it's almost always one of these things, halogen or alcohol plus acid. Find the leaving group, and if the leaving group is attached to, if attached to tertiary carbon, then SN1, right? Make the cation, make the tertiary cation, have the nucleophile attack that. If attached to primary or methyl group, then SN2, right? And remember that SN2 is a concerted mechanism where everything occurs at the same time. Right? If it's attached to a secondary, your work is not done. Then we have to look at nucleophile strength. Right? So nucleophile, of course, is just the base that's going to add to that position. If you have a strong nucleophile, that will favor SN2. Right? Strong nucleophiles are things with negative charge. Right? They have lots of electrons to share. That's always a good thing. You have third row elements. As you go down the periodic table, things tend to get better and better as nucleophiles. So sulfur, right? Sulfur is a very good nucleophile, one of the best. Phosphorus is a good nucleophile, PR3. Or iodine, I minus is actually a very good nucleophile because all of these are kind of low in the periodic table, right? The other thing that that makes strong nucleophiles is less electronegative elements. Right, so things like nitrogen, right? Nitrogen is usually a good nucleophile, right? So strong nucleophiles are things that have negative charge, and or things like nitrogen, sulfur, phosphorus, iodine, things that are lower in the periodic table or a little bit pushed over to the left of the periodic table, closer to carbon, where they're not as electronegative. And the reason that that works is if you're not electronegative, then you're more willing to share your electrons, which is what we want a strong nucleophile to do, right? Weak nucleophiles will, of course, favor SN1 reactions. What are weak nucleophiles? Weak nucleophiles are almost always things like alcohols, right? They're the big ones because neutral oxygen is a very electronegative element. It's not really willing to share its electrons with anything, and so it's not a very good nucleophile. In order to get an alcohol to react with in a SN1 reaction or SN2 reaction, we have to pair it with something that's incredibly electron poor, like a carbocation, right? So alcohols really, most of the time, mostly react with carbocations. Right? So just a real quick example, if we have a secondary carbon that has a leaving group attached to it, the difference in these, right, we did an example before where we used ethylamine, and this was our example of an SN2 reaction, versus if we did this with ethanol. In both cases, you'll get the substitution reaction where this nitrogen replaces the bromine, or in this case, the oxygen replaces the bromine. So in both cases, you can get this reaction to work. It's just that in this one, we would expect this to undergo SN1 because it has a weak nucleophile. Right? And that weak nucleophile is this alcohol. Loss of the leaving group, carbocation. Then we have our nucleophile come in and attack that carbocation. The top one we would expect to go through SN2 reaction because we have a strong nucleophile, we have a nitrogen that's not very electronegative that will add in there and replace this bromine. And so we would expect this to go in a single step, right? I guess we already drew this once, but you've seen this before where the base will come in and attack that carbon and the carbon will allow the bromine to leave. So in both cases, I guess we're also producing Br minus as our leaving group. Right? Both SN2 and SN1 reactions need good leaving groups like bromine that have stable conjugate bases, because in both cases you're losing that leaving group and creating the conjugate base. Right? So SN2 versus SN1 boils down to two things. One, you look at where your leaving group is attached. Right? If you're lucky, it'll be a primary or tertiary carbon. Your decision will already be made for you. If it's attached to a secondary carbon, then you have to look at nucleophile strength and consider, is it negatively charged? Is it a non-electronegative element, et cetera, or is it a neutral compound that has an electronegative element that's acting as the base, like oxygen, in which case you would predict that it would go through a carbocation and be an SN1 reaction. Okay, so that's SN1 versus SN2. We will continue to kind of do more examples of this as we go through more of the more examples of substitution reactions. So more coming.